Hello, this is Mrs. Nearing, and we're going to do a video going over how to find the pH of a polyprotic acid. So this is a handout that you should have from class. You can follow along with me, and there's some practice problems on the back. So if you take a look at this structure right here, this is a sorbic acid, which is vitamin C, something that you're familiar with. And this is actually something known as a polyprotic acid, meaning it has more than one proton, so polyprotic. So poly meaning more than one, protic meaning protons, which are H plus ions, or essentially just protons, right? So that means it has more than one hydrogen it can give. So far all the acids we've been dealing with have been monoprotic. So let's look at how to deal with a polyprotic acid. So the chemical formula is H2C6H6O6. And with these polyprotic acids, we think of the ionizations as occurring in separate steps. So we write out like separate reactions for each of the protons that this acid can lose. So first we want to write out the step for the first ionization of a sorbic acid. So it's going to give up just one hydrogen, and it's going to leave behind HC6H6O6, and now this has a negative charge. And then we can write the equation for the second ionization. So that means you start out at the point where we left off here. So we've already lost one proton. So we're HC6H6O6 with a negative charge. And then this anion is going to lose another proton. So now you're left with just C6H6O6. And now my charge is -2 because I lost another hydrogen. So the K value for the first ionization is 10 to the -5. The K value for the second ionization is 10 to the -12th. So which reaction is producing more hydrogen ions, the first or second ionization energy? The first or second ionization. Explain using our Ka values. So the value of Ka1 is much bigger than the value of Ka2. And so it's like 10 to the 7th bigger. So this is much, much larger. Okay, that means that the first reaction makes a lot more products than the second reaction. Because remember, K is products over reactants. So if you have a much larger K value, you've got a lot more products. And that means that the first reaction is making more hydrogen ions, because hydrogen ion is my product. And it's making a lot more, because again, it's 10 to the 7th bigger. So we're talking several orders of magnitude more from that first reaction. So if we look at B, when predicting the pH of a solution of a polyprotic acid, we treat the solution as if the first step were the only one that contributes to H plus concentration, and use the magnitude of K values to justify this assumption. So basically what we just saw up here is, since the first Ka value is so much bigger than the second Ka value, the amount of H plus made in that second ionization is insignificant or negligible compared to the amount made in that first reaction. So it's like so much smaller that it's not going to make a big difference in my overall pH here. So and looking at the reaction, why do you think this is? So if you take a look, just kind of thinking about, chemical bonding and prior knowledge, why do you think reaction 2 right here is less favorable than reaction 1? Well, if you look at reaction 1, you are losing a hydrogen from a neutral compound. And then what's happening in reaction 2? Well, you are losing a hydrogen from a negative ion. That's making it more negative. So something that's negative is less likely to want to, give up a hydrogen than something that is neutral. So that's the reason why our first ionization typically has a much larger K value than any successive ionizations, because you're trying to remove these protons from more and more negative ions as you go through these ionizations. Okay. So calculate the pH of a 0.050 solution of ascorbic acid, showing your work. So basically, since what we set up here, that the Ka2 value is so much smaller than the Ka1 value, then basically what we do is we just kind of treat it as if it were a monoprotic acid. Okay, so we would, I don't want to scroll up and look at the chemical formula, so I'm going to be lazy and write it this way. Okay, so H2A is going to generate an H plus ion, leaving behind HA minus, and I would use Ka1 to describe this reaction. Okay, and then you set up your ice chart, 0.050, and this starts out at 0, minus x, plus x, plus x. So we just go through and do our regular thing, and we're basically just treating this polyprotic acid as if it were a monoprotic acid, because the amount of hydrogens lost from that second ionization is insignificant compared to how much we lost from the first ionization. 0.050 equals, okay, now I gotta scroll up and look at our Ka1 value, 8 times 10 to the negative fifth. So 8 times 10 to the negative fifth. And remember, we're making this assumption that 0.050 minus x is about the same as 0.050, since k is at least 10 to the third smaller than this starting value. And in this case, we're just barely hitting that standard there, because this we could write as 5 times 10 to the negative second, and this is 10 to the negative fifth, so we're just barely 10 to the third smaller. So anyways, we go through and we would solve for x, which would give us our hydrogen ion concentration, and then to find the pH, we would just take the negative log of that value, and that'll give us the pH of our solution. So again, basically with these polyprotic acids, it's somewhat straightforward. We're just ignoring the second ionization and treating it just like any of our other monoprotic acids that we have dealt with.